Uh, Good afternoon. I am back. Now we will start a new lecture about ocean energy. It's a different matter that the last lecture. And the Professor Paulo Rosa dos Santos from University of Porto that have a lot of experience about that matter. We'll do the lecture. I will read some curriculum about Professor Paulo. Professor Paulo Rosa dos Santos is a professor at the Faculty of Engineering of University of Porto, Portugal, an integrated member of CIMAR, that is an interdisciplinary center of marine and environment research at the University of Porto. His main research field is the use of physical and numerical modeling in the study of offshore, port, and coastal related issues. In the last 5 years, he developed relevant research on the development of technologies to harness wave energy and on the interaction between waves and structures. In the last 15 years, he collaborated in more than 40 R&D projects and consultancy works on coastal, port, and ocean engineering, coastal management, applied hydraulics, and on the development of technology for wave energy conversion. Has more than 70 scientific publications, international peer-reviewed journals, and in proceedings of national and international conference. Participation in more than 45 training courses, seminars, conferences, and congress, review to 7 international indexed journals, energy conversion management, energies, and was member of the scientific committee of 8 conferences and congress. Member of the evaluation committee of 28 Master of Science dissertations and 6 PhD theses, supervisor and co-supervisor of 19 finished master science dissertations and 3 ongoing PhD theses. Member of the board of the Portuguese Water Research Association, North Branch, associate editor of GICZM, the Journal of Integrated Coastal Zone Management Indexes in Scopus. In the last 8 years, he taught in 3 integrated master courses at the FEUP, civil engineering, environmental engineering, and chemical engineering. A wide range of curricular units. In addition, he also teaches in the doctoral program in civil engineering at the FEUP, and was guest professor of the Faculty of Engineering of the Agostinho Neto University in Luanda, Angola, in 2 master courses. Environment Engineering, 2013 to 2015, and hydraulics, water reserves, fluvial hydraulics, urban hydraulics, and coastal engineering, 2014 to 2017. Now I will pass the word to Professor Paulo. We will have 2 lectures today in the afternoon and tomorrow in the afternoon. Okay? Thank you.
Good afternoon. Thank you very much for the kind introduction. First of all, I would like to acknowledge the invitation to be here and to take part on this course, and also to congratulate the organization. It's not easy to organize such a large course, and everything seems perfect, so a lot of work is behind this course, so I think the organization should be congratulated on that. Regarding my participation in this course, it is divided in 4 lectures. Today I will start by an introduction on marine renewable energies. So the idea is to give you a brief overview of the different resources that you may find in the ocean. So I will not have time to go into the details, but at least I think you can learn what kind of resources you have in the ocean and the potential that is available in the ocean. Later in the afternoon, you will have another presentation more focused on tidal energy. I will start by talking about how tides are generated, the resource that is available, etc., and also the technologies that are presently available to harness that type of resource. And tomorrow, 2 lectures that are focused on wave energy. First, about the resource, how waves are generated, how waves are transformed when they propagate from offshore till the shore, etc. And in a second part, I will talk about the technologies that are presently available and the main challenges that we have to harness that kind of resource. But before going to the program that you see here, I would like to briefly present you my university. Only, I think, 3 or 4 minutes. So I came from the University of Porto, in particular from the Faculty of Engineering, that is, of course, in Portugal. So you can see here the campus. This is not the campus of the university, because in our case, the different faculties are spread in the city. So what you are seeing here is the space occupied by the Faculty of Engineering. So all these buildings are the buildings used to the lectures, namely these ones. Here you have the buildings related to the departments where the teachers, officers are, and also some labs. And we also have in the campus buildings that are occupied by research and development centers that work closely with university, and let's say they are an interface with the private sector, let's say. So a picture showing several students very happy to study in FEUP. Just some details. So the faculty was founded in 1926, but the roots are from 1837. So it's an institution with some history, and the Faculty of Engineering is one of the faculties of the University of Porto. You can see here some pictures about the space of the Faculty of Engineering. There we have all these engineering courses, so bioengineering, chemical engineering, civil engineering, well, several courses. I think here you have more or less the same courses we have in Porto. Some figures. So we have more than 500 professors. 93% of them have a PhD. In terms of students, if we combine all, we have in the Faculty of Engineering, about 8,000. In my case, so I work in the civil engineering department that is divided in several divisions. And in my case, I work in the hydraulics, water resources, and environmental division. And within that division, we have a group that works on marine energy. And here you can see the members of that group that works in all the topics related with marine energy. Here you can see another figure presenting the campus. We are based here in this building, and our lab is in this part. Okay, so if you go to Portugal, you are invited to visit us and to see the facilities we have in Portugal, in particular in Porto. And here a close view of our wave basin. Here you also have a wave basin. I have the opportunity to visit the basin yesterday, so they are more or less of the same size. Maybe yours is deeper and ours is a little bit longer, but the dimensions are in general similar. Okay, and here you can see the characteristics of our wave generation system. So it's a multi-element wave maker with 16 independent paddles, so we can create regular, irregular wave conditions. So we are able to simulate in our wave basin the characteristics of the sea. So we can test the technologies before applying the technologies in the sea. So that's the main use of this kind of facilities. And we also have different types of equipment to measure, for instance, the motions of floating bodies, the loads applied in the mooring lines, etc. So we have different kinds of equipments to monitorize the response of the bodies we test in our faculty. Okay, so after this introduction, you already know what we have in Porto, so let's go to the topic of this first lecture. And I will start by presenting some initial questions that we may answer during this lecture. And the first one is, which kind of energy resources we have in the ocean? Do we have an idea which kind of resources we may find in the ocean? Yes? Yes? So waves, tides, wind, so several resources. I will talk more about them later in a next slide. Do you think they are equally important in different parts of the world? No. Perhaps some are more relevant in some countries than others. So I will present some slides that show how the resource of the different resources spreads in the different oceans. The other point is which is the theoretical resource available. How much energy is available on the ocean, and how much energy can we harness from the ocean? So one thing is the theoretical resource, the other thing is the effective resource that we can harness from the ocean. Another point is which technologies are presently available to explore those resources. So I will talk briefly about the different technologies that are available. Do you know if there are some proofs of concept being carried out in your country? Because we are talking about resources that are in a very early stage of development. So a lot of research is being done in different parts of the world, and maybe in your country you maybe also have some work being done and some tests in the sea. Another point that I want to address is how the technologies are developed. So someone has an idea, which are the different development stages from that idea to a demonstration on the sea. And a very important point, how expensive the energy is when it is produced using marine resources. It's a very important point, and we should also talk about this today. So, going to the renewable resources, so we have the waves, of course. You see a lot of waves when you go to the beach, so those waves have energy that can be harnessed. We also have currents that could be related to the tides or not, could be ocean currents. We have the tides, the movement of the water up and down. We have also the thermal energy of the ocean, because the mass of water in the ocean is at different temperatures in the surface and deep in the ocean. And the salinity gradients. So in the mouth of the rivers, when the rivers enter the sea, we have salinity gradients that also are a source of energy. So these are, let's say, what we call the ocean energy resources. But we can also harness other renewable resources in the ocean. Yes? No, it's only the potential available. And those figures may change depending on the source you have. It's not easy to evaluate the amount of energy you have in all those different types of resources. So those values are only an estimation of the resource available. I will talk more about that later, but you can see that the figures are quite large. So the potential available in the ocean is huge, and we should look at that resource and try to harness at least part of that resource. But besides the ocean energy, we can also use the marine space, to harness, for instance, wind energy. So we can install a wind turbine in the sea and explore that resource. And the potential available is also huge, as you can see. But we can also install photovoltaic systems in the ocean. We have a huge space, free space, that can be utilized to install the panels and to harness that energy. It's not so easy as in land, but it's also a possibility. Okay? And we also have the marine biomass. So it's another resource related with the ocean. Okay? So this is just to give you an overview of the different type of resources you have in the ocean. So to have a more clear view, so we can put together waves, tides, ocean currents, the salinity gradients and the thermal gradients in this set, and we call that ocean energy. If we add to that the offshore wind, marine biomass, and eventually the wind, the sun harness in the sea, we have the marine renewable energies. Okay? But we also have these traditional renewable energies. Okay? So this talk is focused on this and this, okay? So the renewable resources that are directly or indirectly related to the sea. Okay? So you know already that the resource available is huge. But one important point is, which is the cost of the energy that is produced using those resources. And as you imagine, at present, the cost of the energy produced by those resources is higher than the energy that is produced with conventional renewable energy resources. So the question is, why to invest money trying to develop those technologies? And one possible reason, a very good one, is that the energy consumption is increasing. The demand is increasing, and we should be able to produce the energy that will be needed in the future. You have here some additional reasons. So the fossil fuels may peak. It's very important to have a diversified energetic mix. So you have here some reasons that justify the research effort that is being done to explore the resources related to the ocean. Here you can see that in more detail. What we can see here is that first, the world population is increasing very fast. You have here some figures. So the energy consumption increases with the increase of population. But another important point is that not only the population is increasing, but also the consumption per capita. So if you combine both, you see that the energy needed is increasing also very, very fast. So we need to rely not only in the traditional sources of energy, but also to look to the more recent resources, and so to look to the marine renewable resources. So they may be expensive at present, since we are, let's say, starting the learning curve, but maybe in a few years from now, they could have a competitive cost. So we need to invest now to have the return some years from now. For instance, you can see here the huge increase of the energy demand. The shale gas may help, but maybe it's not enough. So we should look to other resources and try to compensate with the energy that is that comes from those resources. In addition, by using renewable energies, as you know, we are reducing the emissions of greenhouse gases. So that is good for the planet, and we are also improving the environment. So it's good to have renewables here. And as you easily understand, it is irresponsible presently not to implement changes to mitigate what is now a reality, that is the climate change. So some figures now. If we combine the theoretical resource of all those marine resources, so the contribution from waves, from tides, etc., all together we reach this figure. So here we have all this amount of energy. You can compare this figure with this one. that corresponds to the electricity consumption. And you can see that the theoretical potential is much higher than the world electricity consumption. Okay? Of course, you cannot harness all this energy because the technologies have efficiencies, and efficiency is not 100%, nor close to that value. We cannot install the technologies everywhere, so there are some places that cannot be used. So, but even taking into account that, I think in the future we can supply or we can contribute to a large extent to the electricity consumption in the world. Here you have the primary energy supply, so it's a figure very close to that one. And if you notice, here I am not taking into account the offshore wind, neither the biomass or the energy harnessed in the sea coming from the sun. Okay? So, the use of marine energy can be justified to mitigate climate change effects, of course, to reduce environmental pollution is also a very good reason, to improve the security in energy supply, so the countries can produce their own energy and not being dependent on other countries. For instance, in Portugal, we don't have natural gas or oil, so we have to import those energy resources. So it's good to have energy, renewable energy produced in the country. It also helps to develop the sea economy, so a very important sector. And it could also help us dealing with the variability of the costs of the fossil fuels in the international markets. Okay, so a very good number of reasons to invest and to explore the marine renewable resources. Of course, we have a lot of energy, good energy, but that energy can also be very destructive. So, and the technologies that are on the sea should be able to withstand those very high loadings. You can see here the impact of this wave here and the amount of splash. So imagine technology that has to be in the ocean for 15, 20, 25 years to survive several winters, so it's not easy. So a huge potential, but also huge challenges to transform that destructive energy in something clean and profitable. Okay, so it's a very important challenge. In terms of resource, I will present now some information, some details, and some figures about the resource and how it is spread in the ocean. Starting with the wave energy, you can see here the whole distribution of the annual mean power density. The figures are in kilowatts per meter of wave front. Okay, and these figures are an annual mean. So you can see that different parts of the world have different types of resource. For instance, here around Portugal, we have in medium terms about 40 kilowatts per meter of wavefront. There are some regions here nearby Australia with a huge resource. In Brazil, well, you have not much, but a reasonable value. Okay, so different parts of the world have different resource levels. So looking more close to Portugal, so Portugal is this country here that is nearby Spain. So this is Spain and here is Portugal. So this is a very easy formula to estimate the wave power. We only need to put here the seawater density. You should know this figure. Here we have the gravity acceleration. Here we have the wave height, so the difference between the trough and the crest of the wave. Here the wave period, so is the time interval between two successive crests. And using this expression, we can estimate the power in a wave. And the values will be in watts per meter of wavefront. Okay? In our case, since we are exposed to the Atlantic Ocean, if we make that calculation, we get a value, a mean value for all the year of about 4 kilowatts per meter of wavefront. What do you think? Is a small figure or a large figure? Large. Yeah. And if you have any doubts on that, we can say that if you pick all the power in a wavefront with 2 meters, you have the same power of a normal car. 80 kilowatts, more or less 108 CV. So, and I'm talking about mean values, okay? Not the peak values in the winter, okay? For instance, in Portugal, in the summer we may have waves of 1 meter or even less than that, but during the winter we may have waves of 12 meters or more. So 12 meters is a building with 4 floors. So it's a very large wave. And in Brazil, what do you think about Brazil? Perhaps the waves are smaller. Yeah, I think the sea is more calm here. But on the other side, as far as I know, you have not 750 kilometers, but 10 times that. So the coastline is very large. So I think as homework, let's say, you could try to see in your country, let's say, what is the mean wave and the dimension of the coast, just to have an idea of the potential you have in your country on waves. Okay, so I think it's something easy that you can do very quickly if you use the Google. Okay. Here you have also some figures, so the average values of wave power for different parts of the world. In front of Portugal, about 40 kilowatts per meter of wavefront. If we go north, nearby Ireland and Scotland, we have almost twice that value. If you go to the south, we have a small resource, and here in front of Brazil, maybe something around 20 kilowatts per meter of wavefront. Some values per continent. So the figure for North America, Australia, South America, Africa, Asia, and Europe. So the potential available. So if we combine all the resource around the borders of the different continents. And here the figures for the North Hemisphere and for the South Hemisphere. So it's a huge amount of energy. and here the theoretical resource available. So this figure can change. It depends on the way it is evaluated, but well, even if we choose this figure, it's a huge amount of energy that is available. Here you can have a more clear perspective on Europe. So Portugal has, let's say, a medium resource. It's high, but it's not so high as in this part of Europe, so in Ireland and Scotland. Okay, but there are, you know, in Europe, some areas with a very low wave energy resource. The Mediterranean is not a good place, in principle, for this resource. Although there are some projects being developed for that part of Europe. Sometimes it depends on the technology that is used. In terms of technology, what we can see right now is that unlike what happens in the wind turbines sector, at least in what relates to the onshore installations, where we have, let's say, some standard solutions. So if you are not an expert, all these turbines seem quite similar. But in the case of wave energy, we have a wide variety of technologies. You have here only a few. Tomorrow I'll present more, but each one is different from the other. So instead of standard technologies, we have a very wide variety of technologies. There are more than 1,000 patents of devices to harness wave energy and more than 100 concepts being developed. So just to give you an idea of the variety of concepts that are presently available and being developed. Okay, I don't know if I jumped. Okay. Okay. Another resource that we may found in the ocean is the ocean thermal energy. Okay. So it's related with the temperature in the ocean. And this figure, what presents is the difference of temperature between the surface waters and the waters that are 1 kilometer below the surface. And we can see that the locations where the difference is higher are around here, okay, where the water at the surface is higher, because in the deeps of the ocean the water temperature is more or less the same in the different parts of the world. So this type of technologies take advantage of the temperature difference between the surface and the water nearby the bottom, and that difference should be at least 20 degrees. So we can see here that the most interesting locations to harness this resource are these locations here. So the locations where you see the yellow and orange or red color. Okay, so it's not a good resource to be harnessed in Europe, at least in this part of Europe, but it could be a good option for other countries in the world. Although it's a domain that is also in a very early stage of development. Okay. So the best locations are usually located in the tropics, where the ocean surface water is around 27 to 29 degrees. The potential associated to this source of energy is very high. You can see here 44,000 megawatts hour per year. So a huge resource. but is not a good resource for Europe. As you can see here, only some overseas territories have an interesting resource. Well, the technologies available can be grouped in these three types. The closed cycle here, usually ammonia is used in the process, and the open cycle system where water is used, and there are also some technologies that combine both. Another resource is the salinity gradient. So we have here a river mouth. Here we have the sea, so fresh water, salt water. So there is a difference in the concentration of salt, and that difference of concentration can be transformed in a source of energy. So the salinity of water is around this figure here, the seawater around that, so we can explore that difference. Here you can see a figure that shows how the salinity varies in the ocean. So there are some parts of the ocean with a higher concentration of salt than others. And you can see here some potential, not only for the world, but also for Europe. So these technologies explore the salinity gradients and make use the differences in terms of osmotic pressure between the waters with a different salt content. In terms of technologies, we have the pressure retarded osmosis. So as you may know, if we have fresh water and salt water, water tends to cross this membrane and go from here to there. Okay, so this results in a pressure increase, and that energy can be converted into electricity by a proper system. It is also possible to take advantage of the chemical potential between both solutions. So in this case, let's say is a chemical way of harness that kind of energetic resource. The drawback of these technologies is that both rely on specific membranes that are very expensive, and the efficiencies are not so good as we would like them to be. So it's a critical point of this system. So the main barriers to development, let's say, are of course the membranes that are required in both systems, and their performance that is not higher, is not high at this moment. In addition, nearby the power station, we are discharging water with a high salt content in a water with a lower salt content, so we could have some impact there. It's not a big impact, but it could be mentioned as an impact. But there are some research being done in UK, Norway, and United States, and research started more or less in the 70s, as far as I know. As I mentioned initially, we can also harness wind at sea. If you have a flight that crosses the North Sea, and if there are no clouds in the sky and you look below, you can see some offshore parks already installed in the North Sea with several hundreds of wind turbines, like in this case here. In fact, the resource available in the North Sea is high in terms of wind energy. So you can see here that the red and blue color are associated to high wind speeds. So we have a good wind potential there. And in addition, the water depths, at least in some parts of the North Sea, are not too high. So it is possible to use piles that are fixed in the sea bottom to support the wind turbine. And so we have already some commercial wind parks in the North Sea in operation. So the main challenge now is to develop suitable and cost-effective solutions to harness wind energy in deep waters, because in deep waters is not a good idea to install a very large pile, because it will be very costly, and that will have an impact in the cost of the energy that is produced that way. Here you can have a world perspective. So what you have here is the wind speed at the height of 10 meters. So there is the North Sea, where most of the parks are. Portugal, Brazil. So, well, the resource is not extremely high, but is high enough to justify the development of technologies for that kind of applications. Here you have the locations of the parks that are already in operation, under construction and proposed. So most of them are here in the North Sea, a few here in the United States, and also in this part of Asia. Okay? So there are already a number of large-scale projects nowadays running, especially nearby UK and in the North Sea. And motivation for that, because it is more expensive to install a wind turbine in the sea than inland, is that in the sea, open sea, we have more stable and more strong winds. Okay, and so that's the main motivation to go to the sea. In addition, there are also some limitations in terms of the size of the turbines that we can install inland that we do not have in sea, because it's easier to transport the turbine in a boat than in a truck to install the turbine in the top of a mountain. So there are some constraints that we do not have in the sea that justify all these investments to install wind turbines in the sea. However, the sea also presents some new challenges. As I mentioned before, it's more difficult to install the turbines in the sea and to ensure they are operating well during their lifetime. The maintenance operations are more difficult to perform in the sea than inland. So there are additional technological needs and challenges for this kind of applications. Well, it's also worth mentioning that most of the technologies being used in this kind of parks came from the oil and gas industry and from the traditional wind power industry. So we are combining knowledge that comes from two very different sectors. Well, to have an idea of the trends, I have here this graphic that shows how the installed capacity changed from 1993 till 2015. And so you can see that the increase in installed capacity was very quick. From the beginning till here, a very huge increase in terms of installed capacity. And this trend should continue in the future. So 2015, 2030, and you see that the trend is expected to continue in the future. So a lot of investment in this area. And of course, the cost of the energy tends to reduce as the scale of the sector increases, what is good. We can also see here in this figure information about the distance to the shore and the information in terms of water depths in the locations where the parks are installed. So what we can see is that most of the parks are nearby the coast. So in that case, we need a shorter submarine cable to transport the energy to the shore. And in addition, usually we have smaller water depths, so it is easier to install the supporting pile there. But in spite of that, we also have some projects foreseen and already installed far away from the shore, in this case about 70 miles, and in very deep waters, about 90 meters, and in this case a demonstration plant in Portugal in a water depth of about 50 meters. Okay, so in Portugal we have very high water depths nearby the coast, so typically the solutions that are used in the North Sea are not suitable for our coast. So what is done is to try to develop floating solutions to give support to the wind turbines. So this is a demonstration project that ran between 2011 till 2016. 2 megawatts turbine, floating turbine, and here we have another project, if I'm not wrong, maybe nearby Norway. So the harvestable energy available is very high. You have here some figures, some estimations for 2020 and 2030. And here you can see the different technologies available to support wind turbines. So nearby the coast, the most usual solution is to install a pile, what we call a monopile, a single pile, to support the turbine. For larger water depths, maybe better to install a tripod or a jacket structure like this one. In deep waters, the tension leg platform or the semi-submersible platform, and for very high water depths, the spar buoy. So depending on the water depths, we have different supporting structures. So initially, all the parks were based on these kind of solutions. A lot of research is being done regarding demonstration in the sea of this kind of solutions, because they are the only ones available for deep water locations. That is clear here. In this figure, you have here the water depth, and here the cost, and here the price, how the price changes with water depth. So you can see that the monopile, after let's say 25, 30 meters, is not more cost competitive with this kind of solutions, and after 50, 60 meters, only the floating structures are cost competitive. Now, some overview of the most well-known technologies. We have here the SPARBOY system, a tension leg platform system, and a semi-submersible system. So I'll start by the wind float. This concept is being developed by a consortium where ADP, the Portuguese electricity company, is a major partner, and was developed and installed offshore the Portuguese coast. You can see here some pictures showing the transportation and installation of the floating platform. And this kind of technology is suitable for water depths higher than 40 meters. So it cannot be applied at smaller water depths. Is a solution that is very easy to transport. So all this is stable. You can use a tug to push the turbine to the place and then to moor that to the sea bottom. Usually this is the different parts are assembled in a shipyard, so you can put all the parts together in land and then to transport the turbine with the supporting structure to the sea. These kind of solutions may have larger movements than a tension leg platform that I will present next. And also they are more heavy, so you need to use more steel to build this kind of solutions. So that's one drawback. But they are more stable and able to support higher waves than the other ones. Yeah. I will present a video in about 2 slides that shows all the process from the construction in the shipyard till the installation and mooring in the sea, and also how the ballast in these piles is adjusted to compensate the load distribution in the structure. A potential drawback is that the footprint of this solution is larger than in the other cases, because we need some mooring lines and we occupy some areas in the sea bottom. Some challenges to control movements and accelerations, and let's say to avoid some resonance effects with waves, and of course to reduce the weight and cost of the structure. The initial structures were designed following more or less the codes that are used in the oil and gas industry, so very conservative designs, and so perhaps the future installations will have a different design, a less expensive design, because the risks here are not so large as in the oil and gas sector. So here you have a video that presents all the process from the installation in the shipyard or inside a port till the installation in the sea. So you can see the different parts being put together. it's easier to build this on land than in the sea. Where is the? Sorry? In this case was in Portugal. Setúbal. South part. But in that case was only for one, because was the wind float demonstration project. This is a video that intends to present all the process, but it's not a real video. It's an animation to show how the process is done. So here you have a park with several turbines. And the tugboat pushing the new one. You have some boys here. They are connected to that. They are associated to the mooring system. If we put some water inside these parts, we have the sinking of the structure. And yeah, the ballast to control the position of the platform, especially because the wind may change direction and it's important to maintain the turbine working properly. These plates are to reduce the heave motion. And you can see the mooring cables and also the electrical cables that transport the energy to a substation and then to the shore. So the demonstration project run very well, and so very shortly a new installation will be done in Portugal, nearby Viana do Castelo. This time not a single element, but a small park with 3 or 4 wind floats. The other option is the tension leg platform. So it's a different concept. It's a lighter concept, as you can see here. But the price to pay is that in this case, the construction and the installation are more difficult and more costly. So you save in steel cost, but you have more difficult and complex operations in the sea. Is a solution that is suitable for water depths above 50 meters. The movements are not large, but it requires a complex and expensive mooring system, and we need some redundancy because this solution is not stable without the tensioned mooring system. So we need some redundancy to ensure that the structure is stable. On the other side, the space occupied is smaller, so the footprint in the bottom is much smaller than in the case of the wind float. Challenges, well, to develop simple and less expensive mooring systems. One question? Okay, sorry.
Okay. My name is Ulisses. I'm from Brazil, and I know that the offshore wind is an alternative to energy, but in Brazil, the cost of the special cable is very high, and in the offshore wind, how much the percentual cost of the the cost of the installation represent the cost of the cable in the installation, and if for the values justify the installation in offshore and not in onshore.
Well, it's a good question. I don't have a specific number for that, and that cost also depends on the local conditions. So the costs may change from one location to the other. But the main motivation to invest in this kind of projects is that in the sea, typically we have more strong and stable winds. And we can also install in the sea large turbines, because the installations inland are somehow limited by the trucks that transport the different parts of the turbines to the top of the mountain for the installation. In the sea, you don't have that type of constraints. You can build the components in a factory nearby the port to put those components in the boat and to transport that to the installation site. So the dimension of the wind turbines in the sea is increasing very fast in order to reduce the cost of the energy. At present, I will present later some figures. This energy is not, well, it's a little bit more expensive than the energy produced onshore at the moment, but the prices are going down, and very shortly, possibly, they will be very similar. And the other reason is that in some countries, the good places for the installation of wind parks inland do not exist anymore. If you go to Portugal, we have several wind parks in our mountains. So it's difficult right now to see one mountain without the wind turbines. And so if we install the turbines in the sea, you don't have that visual impact. Okay, so there are several reasons that justify this kind of investments. Of course, we have some extra costs, and the cost of the cable, of course, is a very important part, but we also have some advantages, and if you put all that together, you may have a benefit. And well, presently these projects are being developed by the private sector, and they only invest if they feel that they are going to have a return. And if you see the increase of the installed capacity on sea, so they see a lot of potential on that. Okay. Well, you well, that's a difficult question. Well, maybe, I don't know, 10 miles, 15 miles. But there are also other constraints. So there are some areas nearby the coast that are protected because of biodiversity reasons. There are also navigation routes. So we cannot install wind parks where we want. So there are some areas available, but not all the space. But these projects should have a study, an environmental study, and an impact study to analyze all the details before they are implemented. Okay.
Yeah, I have just a question about the submarine cable. Are we limited with the size of a submarine cable? For example, if we have a lot of power or a lot of currents, can we have any size with the submarine cable, or are we limited?
Yeah, well, the submarine cable should be protected. For instance, a very critical part is the part of the cable nearby the breaking zone, where the waves break. Because in that location, when the waves break, you have a lot of sediment movement, and so the sea bottom is unstable. It can change a lot. So it's better to bury the cable there to protect the cable. And that may also be valid in deeper waters because of the action of currents. But in this case, each case is a different case. So it's necessary first to make some studies, to analyze the currents on site, to analyze the waves, so to analyze all the details before design the protection for the cable. Okay, because we want the cable to be stable and not having any problems in the future on that. But the actions on the cable depend a lot on the local environmental conditions on site. And the critical part is in the breaking zone, so where the sea bottom is very variable, where morphological changes are very significant. Any more questions? Yes?
Erica from Brazil. Tell us more about the maintenance. How is the interaction with the marine life, the animals? How is the frequency to clean the structure and to grow in algae?
It's a very good question, and I have some slides in the end of the presentation. Yeah. Yeah. Yeah, I have some slides that address that topic. So the marine growth and also the maintenance operations that are, of course, more difficult in offshore than in the shore. But I will talk more about that later in this presentation. Okay, thank you. So moving to the other concept, so the spar buoy. So in this case, we have, let's say, a floating pile. So something like this with a turbine on top. So it does not seem very stable, but in fact is a solution to support the wind turbine. This kind of solutions is suitable for water depths between or above 120 or 150 meters, so large water depths. Well, it's very important to control the roll and pitch movements, so we should control the amount of movements the support has. One critical point of this concept is the installation. So it's much more difficult to install this in the sea than, for instance, the semi-submersible type of structure. So some challenges are to control the movements of the turbine, to reduce fatigue, and to develop suitable, less costly and complex transport and installation techniques. I will present also a video to show you how complex the installation of these turbines is. So you can compare the difficulty of this installation with the case you have seen before about the wind float. So you can see here a picture, so you can see the spar buoy, so a very thin pile. It seems more thin than actually it is, so you can have piles with a diameter of 8, 9 or even more meters, but they are very high, maybe 60, 70 or 80 meters. And to maintain this in place, we need some mooring lines. for station keeping, and we need to put a lot of ballast here for stability reasons. So the only way to maintain this pile vertically in the ocean is to reduce the center of mass, and that is ensured by installing a lot of ballast here. A picture showing the installation, and now a video that shows all the process. So it's a similar video, but in this case for the spar buoy. This concept is being developed by a company from Norway, from Statoil. So that is an oil company that has a division that is focused on the new energies, let's say. So maybe they are preparing for the future, I don't know. So you can see the transportation of the different parts of the turbine, but the assemblage of that parts has to be done in the sea. And very specialized boats are required for the installation. You see, instead of only one tugboat, you have there 3. So a more complex procedure. And here another boat. So this installation takes more time and more people also. Now some ballast to increase the draft of the spar buoy. Then it is pushed to that supporting boat. So you can see the length of the part that is below water, so several meters below water. Now some solid ballast, for instance concrete, being placed inside. So it's very important to put a lot of ballast in the bottom. These videos have some sound, but in this case it's not possible to hear that. So now some components for the upper structure that should be put together also in the sea. So the sea should be very quiet, otherwise it is very difficult to fix all the components together. So it's a more complex installation. Yeah, it's metallic, usually steel. can see that a lot of operations should be carried out with a very high precision. And so it takes more time. And specialized vessels are needed. So ships specialized to transport all these components to the sea and to put all of those components together. A large part of the structure is below water. Okay, so I think the most important parts were already shown. Okay. So, in terms of water depths and wave conditions. For the rougher wave conditions, the best solution is the semi-submersible platform. So this structure was installed 5 years offshore the Portuguese coast and was able to successfully withstand 5 winters with very high waves. So it's a good solution for that kind of applications. And for water depths above 40 meters. If you have larger water depths and waves not too high, you may decide to adopt the spar buoy system, and the tension leg platform is more or less in between the two solutions. Here you can see some comparison between the three concepts and the developing stages. So you can see here, I think we cannot read properly here, but well, this is mostly related with the development stages and the demonstration in the sea. And we can see here that the most developed ones are the spar buoy solution and the semi-submersible solution. Because if I'm not wrong, this color here represents the demonstration in the sea, but I cannot read properly from here. So I presented 3 different solutions, but there are other technologies being developed. So you can see here other concepts being developed in those 3 categories of supporting structures. But the most developed ones are the wind float, a consortium between a Portuguese company and an American company, and the high wind technology of the spar buoy type being developed in Norway. So you can see here the different developing stages, so the concept development, scale testing, full-scale prototype, and the pre-commercial stage. So it's where these two technologies already are. So they are not in the commercial phase, but very close to that. And there are other options approaching also that phase. This slide here is to show you that besides the typical turbine, there are also some other solutions being idealized and tested. We have here this concept. So instead of horizontal axis of rotation, we have a vertical one. Okay. The advantage of this option is that let's say the core part of the turbine is at a lower elevation, so it's more easier to make the maintenance of the technology. So you can compare the dimension of the boat that is required to give support to those operations. In this case, the boat is much larger than in that case. Another advantage is that in this case, if the wind changes direction, the turbine also needs to change the direction to produce effectively energy. In this case, there is no difference. So since the rotation is along a vertical axis. So this is the typical solution, but other solutions are being idealized and tested, and perhaps in the future we may find this kind of installations in the sea. Well, here you can see the evolution in terms of dimensions. Not only the dimensions of the turbine rotor, but also the increase in terms of the rated power of the turbines. So now we already have turbines above 5 megawatts, but much higher figures are expected in the near future. And installations in the sea have less constraints since it's more easy to install big components in the sea than inland, especially due to the transportation in highways and to put everything in the mountain. Some challenges also related with the materials suitable for such large turbines. A new project that is also being developed by a consortium that includes a Portuguese company is the Demo Gravi project. In this case, the idea is to develop a new supporting structure for turbines for water depths above the usual application water depths of the monopiles. It is based on a gravity solution. In this case, we have three supports, concrete supports. The structure is being idealized to float by itself in order to be transported to the installation site this way, so with the assistance of a tugboat, and then with help of some ballast, the turbine can go down and be installed in place. So the idea is to have, let's say, an alternative to the semi-submersible platforms for water depths of around 50 meters or a little bit above or below that figure. Well, some information about the levelized cost of energy. Well, here the idea is to show how that parameter, economical parameter, varied along the time. You can see that early in the 80s, the onshore wind was an expensive energy resource, but now is cost competitive with the traditional sources, because there was a lot of research, a lot of improvements, and that made possible to come from this point to this point. Okay. In the offshore wind, we started later in Denmark with some offshore parks very close to the coast. Now we are moving to larger water depths, but maybe in the future we can also get a cost competitive price with traditional energy sources. So before the break, I will talk briefly about this economical parameter, because we are usually talking about the cost of the energy, the cost of the electricity, and I think it's important for you to have an idea how this parameter is calculated. So the LCOE is, let's say, a standard in this sector to define the cost of the electricity, and it is calculated considering all the costs in the life cycle of the installation, and considering also all the energy that is produced in that period. So, for instance, if you are talking about a technology to be installed in the sea, we should take into account not only the capital costs related to the construction of the device, to the foundation in the sea, to the moorings, connections, the design is also a cost that should be taken into account, the commissioning, but also the operational costs to maintain the farm operating in the sea, maintenance, operation, insurance, eventually seabed renting and transmission charges. And we also take into account the energy that is produced. Okay, so is a very good metric to assess the real cost of the energy that is produced. And we can also take into account inflation in the analysis and discount it to account for the time value of the money. You can see here the equation. So in the upper part, the sum of the costs over the lifetime of the installation. So we put there everything. So the initial investment costs, the operation and maintenance costs, fuel in some cases. In the case of the renewables, we don't have fuel costs. That's one of the advantages. And in this part here, we should put the electricity that is produced over the lifetime of the installation, and the result is the levelized cost of the energy or the electricity. Here we can see how that parameter varies for different types of renewables. In this case, we should take a more detailed look on the onshore wind, 50 to 70 euros per megawatt. The offshore wind, that is higher, and the waves that are in an earlier development stage with costs much higher than the offshore wind and the onshore wind. Okay, but maybe in 5 or 10 years this figure will be different because the research development usually leads to a reduction of the costs and to more and to smaller levelized costs of energy. So the LCOE can also be regarded as the minimum cost at which energy should be sold to break even over the lifetime of the project. So it's a good reference for this kind of analysis. In this case, we have a similar representation, but here what we can see is the division taking into account the different components. So we have the fuel. In cases we need to take into account that. For instance, in these cases we have some fuel costs. Here we don't have because they are renewables. And also the fixed operation and maintenance, the variable operation and maintenance, the commissioning. So all the parts are represented here, and you can see that in general offshore energies present a higher LCOE than solar, onshore, or other sources of energy. Uh, 2015. I think, yeah, in this case, yeah, it's 2015. So, well, it's usual to have different values depending on the source. So I think the most important here is to have an idea of the relative values. And what you should retain here is that marine renewable energies in general are more expensive than the other renewables. But this is the present situation, so maybe in the future this will change, and maybe we could have a cost competitive energy. Another graphic, you can see these in more detail after, because the presentations will be given to you later. Here you can see another estimation of the LCOE and how it varied along time with the increase of the dimensions of the turbines. Here you can see from another source other values, not only the present values but also the expected values in the future. But as I said before, these values change a lot depending on the source you are considering. Okay. So there are learning curves for each resource and this technology.
May I have a question? You are showing us what you think it's like a trend to decrease the value of this kind of solution. From our past lectures, for example, in the PV system, what made it cost decrease was China tried to manufacture almost everything in that. When you show it to us, the main manufacturers, I didn't see anyone from China. I see from a lot of countries. Okay, but do you expect that the decrease in the cost, how do you expect that it happens by a lot of people, a lot of countries manufacture, or like China to decide to make everything?
Yeah, it's a good question. In this kind of technologies, the steel is perhaps one of the main components, and it has a price in international markets, and so possibly the cost reduction is somehow limited by that price. But maybe in the future new materials could be used with similar or even improved properties, and so that could result in a reduction of the cost. Well, it's very difficult to predict what is going to happen in the future, but once more research is done, more experience is obtained from the sea installations, and as far as we increase the number of installations, there is a scale effect. So what I can say is that we should expect a reduction in the future. Of course, if China decides to invest in a very strong way in this sector, of course, the prices will go down faster than the other way. But it's very difficult to predict what is going to happen in the future. Well, here we have again the reduction of the LCOE for the onshore wind. So a very large reduction. And here the cost of the solar photovoltaics also a very large reduction.
Good afternoon, sir. My name is Bruno from